more general than what I suggested at the beginning. So I want to look at randomization for clustering tasks. I'm working a lot on clustering, and I want to, and in some tasks, randomization helps. So I'll talk about two clustering tasks and how randomization provably helps there. So, how do you, oh, please down? Down?
Yeah.
Okay. So finding optimal clustering is known to be computationally infeasible. Many popular, if you have clustering which is directed by some objective functions, then for most of the common objective functions, finding the optimal clustering is NP-hard. And the big question is how can we do clustering efficiently, because it's a very practical task. And so for some of those tasks, we can show that randomization really allows to design polynomial time approximation schemes. So you have a clustering task like k-means, k-median. I will show several of these, and they're NP-hard, and you want to approximate it efficiently. So I will discuss two clustering tasks. One of them is a family of center-based clustering objectives that includes k-means, and the other one is a task of co-clustering, in which you have a different type of clustering. I don't know how much you know about co-clustering. I'll explain it when I get there. So I'm talking about two types, two families of clustering tasks, and how randomization is going to help to overcome the computational difficulties of both. So let's start by the basic idea. The basic idea is that you want to do sample-based clustering. So you have a big data set, you want to cluster it, and it's too big to process. Therefore, you just take a sample of your data. So we know what the motivation is, and we need fast clustering algorithms. Not only is NP-hard, but even linear time or quadratic time algorithms may be too expensive when the data is very big. So we propose clustering-based, sampling-based. So this is where the randomization comes in. We just take a sample of the data and cluster it. Okay, so the first example is center-based clustering. So center-based clustering is the big family of clusterings. What I call center-based, let's call it center-based if the clustering is determined by some center points. So you pick some representatives of each sample, and then you cluster according to the induced Voronoi diagram. So these are center-based clustering, and this family includes k-median clustering and vector quantization and many other popular clustering schemes. So these are clusterings in which you just have to pick typical elements from each cluster, and then you do the Voronoi diagram, and that defines your clustering. So for these clustering tasks, we can show that randomization really helps. So what is the basic algorithmic idea? We draw a random sample of the input data set. You have this big data set. Then you find a group clustering of the sample. Because the sample is small, the sample size does not need to depend on the input data, only on the approximation parameters. So you can find the optimal clustering for the sample, and then you extend the sample clustering to the full data. And here we take advantage of the fact that it's center-based. Because if I have a clustering of a sample, it's not always clear how do I induce a sampling of a clustering of the whole data. But if it is center-based, I just take the centers that worked for the sample and use them as centers for the whole data set. So that allows me to extend clustering of the sample to clustering of the full data set. So the main source of success here is that center-based clustering. So why? I mean, the big question is, if I do this kind of paradigm, what kind of guarantee do I have that the clustering that I get from the sample is really good for the whole data set? And it really depends on final properties. Okay. I mean, the first one that collapsed was the one that claimed that it's embarrassed in parallel. So it became not parallel. Okay, so the question is, when can we guarantee that the sampling-based clustering will give me a good approximation to the best clustering for the data set? And I want to mention what is the main idea. So the main idea is that center-based clustering has a compact representation. So if I cluster, if the if I want the centers to be members of the data set, then of course you get the data set, you can represent the clustering by just those k-many points that you use in centers. So it has a very compact clustering. But even, very compact representation. But even when the centers are not necessarily have to be members of your input set, you can still give it compact representation, so that's a bit trickier, but still intuitively it's clear that if the clustering is center-based, all you have to do in order to represent the full clustering is just to give me the center points. And this compression ability, this ability to represent your solution in a compact way, allows us to prove uniform convergence results. Uniform convergence means that no matter what the data set is, if you take samples which have size that depends only on the accuracy parameters, you can get a guarantee of the approximation. There's one caution here, it's a question of in what sense do you want to approximate the optimal clustering. So if you want to approximate the optimal clustering in the sense that the clusterings will look similar, then this is going to fail. This is stability that we worked with David, and we showed that you cannot assess the structure of the clusters. But we can approximate, and that's what we show here, is you get a clustering with a similar cost. So it may not look like the original clustering, but if what you care about is the cost of clustering, you'll get something with a very close cost. Okay, so the results that we get, if you compare it to previous results, the main point is that we get the first constant time bound, running time bound for the approximation without any restrictions on the data set. So we get running time, which is, you see, what we don't have here is the input size. No matter what your input size, your running time is going to depend only on the approximation parameters and the number of clusters. So it's a constant time approximation. You get, if you want to be epsilon close to the optimal cost, this is the running time that you will need to find these centers. And this is the first result of its kind that just gets constant time for k-means, for k-median, for any center-based cluster. Okay, so now let me go to the second problem. So that was one problem, center-based clustering. We have a compact representation, and we can use uniform convergence techniques to solve it from samples. The other problem is co-clustering. So co-clustering is less familiar, so let me describe the problem a little bit. So assume that you have to consider the task of clustering university web pages based off the graph of links between the pages. So you get the university, the whole collection of web pages of the university, and you want to detect groups. And the way to detect groups, I mean, if you want to detect the group of professors, what's similar between them is not that they are close to being a clique. The professors in the university don't link to each other, usually. But what may be similar is the pattern in which they link to the rest of the web pages. So you get such a graph of the web pages of the university. You want to cluster nodes according to the pattern of links that they have. And so we wish to find clusters of functionally similar groups, not groups that are clicked together. Okay, so here oh, that's a very bad, the graphics are very bad, but an area where this is very common is the area of gene expression microarrays. So here you have different genes, and you have different treatments, and you get the brightness response to how much the gene is activated by this treatment, and you want to group the genes and the treatments in such a way that you will get genes that correspond similarly to treatment will be grouped together, because this may indicate that they are functionally similar. So we get a matrix which is kind of a gray mixture of zeros and ones. You want to reorder the columns and reorder the rows in such a way that it will look like a chessboard, that every block will be either bright or dark. That's the kind of co-clustering. So we have two types of elements, and we have some measurements of interactions, and we want to group them together such that it will be, the blocks will be as homogeneous as possible. So that's a co-clustering task. And we formalize it, so we want to formalize it, so your input is a matrix of 0, 1s, and you want to find, and you're also given the number of row clusters and number of column clusters, and you want to find the partition of the columns and partition of the row, such that the resulting blocks will be as homogeneous as possible. So the cost that you are trying to minimize, we call it the monochromatic cost, is the number of entries that are in the minimal value of the block. So if you have a block that has majority white, you are penalized for every black entry, and if you have a block which is majority black, you're penalized for every white entry. So that's a very natural cost function for this type of task. You want to make the blocks as homogeneous as possible. So the number of blocks is given to you, the matrix is given to you, you want to make them as homogeneous as possible. And here, we can think of it as some compression of the matrix. Instead of giving you the full matrix, I can give you just the matrix of blocks, and then, of course, it's much compressed. All you need to know is to which block your entry belongs, and the monochromatic cost is just the error or the distortion of this compression. So it's a very natural objective for compression. It is minimize the distortion given this size of compression. And the first result was it is really NP hard, which everybody, I mean, it is not surprising. Most of the clustering tasks are NP hard. And then the randomized part is that we show the randomized algorithm that has running times which is almost linear. So the matrix size is n times n, and here we have an exponential factor. It's a kind of parameterized complexity. So we have an exponential factor. It exponentially depends on the approximation accuracy and on the number of log of the number of row and column clusters. But in general, it's except for this factor doesn't depend on the input size, and the dependence on input size is linear. So you get a randomization. We can probably get a very efficient approximation to this bi-clustering, to the optimal bi-clustering. And the cost after this running time, the cost is the optimal cost plus this epsilon here. So let me give you just the idea of what is the approximation algorithm. And again, we do it by randomization. So we picked randomly, we pick T. T is determined by your approximation accuracy, the epsilon you're shooting for. You pick randomly T columns, you pick randomly T rows, but now you do something very different than before. Before we picked a random sample and we found the optimal partitioning of the random sample. Here we pick a random set of rows and a random set of columns, we get a small matrix. For this small matrix, we look at all possible partitioning of this matrix. And for each of these partitioning, we extend it to the full matrix. So what is happening now is that, so for each partitioning, we extend it to the full matrix, we go over all of them and pick the one that has the minimum cost of the full matrix. So we cannot prove here that the cost of the small matrix will approximate the cost of the big matrix. We have to exhaustively look at all the solutions for the small matrix, and they kind of create a cover that approximate every good solution, every potentially good solution of the big matrix. So in words, what we do is we consider all solutions that are induced by co-clustering of the random sample, and we show that with high probability over the picking the random rows and random columns, if you go over the partitionings that are induced by solutions for the small sample, you get an epsilon cover of the space of all partitions. By epsilon cover, I mean every partitioning of the big data set has a partitioning which costs at most epsilon away from it that is induced by the sample. So going over the all sample-induced partitionings give you, and that's why we get this, you see the type of the shape of the form of the bound. This is exponentially many. I mean, the sample, the size of the run of the sample depends on epsilon. We're exponentially the size of the sample because we do exhaustively all partitioning of the sample. For each of them, we just have to multiply it by the matrix size to see what it induces over the whole matrix. Okay, so the summary is that we have two different approaches to design randomized clustering algorithms. The first approach for center-based clustering uses uniform convergence. If your clustering can have a compact representation, then you can apply compression ideas to show uniform convergence. So you just look at samples, do optimal sampling, clustering of the sample, and extend it to the full cluster. The other idea is a completely different idea. You take a sample, you look at all possible solutions for the sample, you extend each of them, and you have a guarantee that it will kind of cover the space. And I think this one is more, this is very common in machine learning. This is a kind of a different idea, which I hope that there will be more applications to it. So, thank you very much.
Any questions?